Hello, my name is Mark Case, and today we're going to be taking a look at an experiment that is going to try to calculate the empirical formula of a compound and also of a hydrated substance. This is a common experiment that students will have to be able to use, but in this case, we're trying to get something that will not have a definite answer that they can look up, such as magnesium oxide is a common one, where it should be a 1-to-1 ratio just by looking at the charges. The first part of this is going to be using a reaction of manganese, and that's going to be combining with hydrochloric acid, which will provide chloride ions. And if the student looks at possible oxidation states, they will find that manganese could be a +2. That's a very common oxidation state, but it could also be a +3, or you could find that it would be a +4 or a +6 or a +7. The chlorine, on the other hand, is usually -1 as a chloride, but there are compounds where chlorine is bound onto the oxygen, in which case it sometimes has a +1, a +3, a +5, a +7. So it creates a little bit more options that the student could look at as a possibility of what is the formula that's going to be generated. For this reaction, we begin by starting with a 100 milliliter beaker, and we use a watch glass just to try to contain some of the vapors that are coming off from that, and also during the part of initially heating it up, so it prevents any spatterings. So you can mass a 100 milliliter beaker and the watch glass as a lid. You are then going to add to it about 1.0 to 1.2 grams of manganese metal, and this should go into that beaker and then remass that again with the lid, the watch glass, if you're going to use it in that fashion. In this case, I used a fairly large piece. I didn't break it down to speed up the reaction, since you don't want to be here all day doing this. You can take a pair of pliers and then just take that piece of magnesium and break it up into smaller pieces by squeezing it and snapping it off. It occurs pretty quickly and pretty easily, but that's going to be your starting experiment that you're going to work with. Now, you're going to add to this 10 milliliters of hydrochloric acid, which I tell the students that this is just going to be in an excess amount so that they know that they're going to end up getting a complete reaction occurring, or they should get a complete reaction occurring, even if they use the 1.2 grams up to maybe a 1.3 gram value of manganese metal. The acid strength that we are using here is 6 molar. And if necessary, you could actually use 3 molar. And then after the initial reaction occurs and it slows down, you might have to add a little bit more to it. I'd rather just use the 6 molar and go from there and get the results. So I'm not trying to tell them what the answers are, but 6 molar will be plenty of the material that you need available. This is actually the reaction that occurs. So if I take a look at this video here and start that, by adding the 10 milliliters of hydrochloric, and that amount is not an exact quantity, you don't have to worry about having that exact value, but it's very vigorous bubbling that initially occurs. And this is why the watch glass goes on, to try to avoid some spattering. This will go on for quite a long time because it's a fairly large piece. So you're looking at a half hour or more for this reaction to occur. We can speed that up a little bit. So I'm going to bump up that rate so that it goes a lot faster. Eventually, the bubbling would subside or start to slow down. And that's because you are using up the hydrochloric acid. So in kinetics, you have less of the particles of chloride that can collide with and interact with the manganese and start to bind to it. Notice that there is some vapor that is generated, and that again is why the watch glass is there. In some cases, we can do this under the fume hood to minimize any initial vapors that might come off, which will be mostly the hydrogen gas and a little bit of aqueous water vapor, but it may bring with it some hydrogen chloride that's in there. So you might want to do it under a fume hood if you have that available for you to work with. Now, while this is taking place, what I normally have my students do is go on to part 2. Now, part 2, what that particular reaction is is that you're going to be using a hydrated compound. In this case, we're going to use something that you can find around the house, and that is just using Epsom salt. Epsom salt is magnesium sulfate, and we don't know exactly how much water is in there, so we'll just say that's X amount. So what I'm trying to find in this case is the proportion between magnesium sulfate plus the water that's in there. So let me pause at this point because I want to show you the video that's set up for that, and then we'll go from there. Now, the Epsom salt is already made up, so you don't have any kind of reaction going on. This is more of a physical separation of the water molecules as we dehydrate that. And in order for this to occur, you have to have a temperature in excess of 300 degrees. Some say 250, but you'll find that if you don't have a high enough temperature, it's only going to partially dehydrate. This is where I would normally like to use a Bunsen burner as a preferable method of heating it, because it will be able to allow me to get to a much faster decomposition and drying out that water vapor. So you see, initially, I don't have the watch glass on top. That's just so that you can see that as it's heating up at 300 degrees Celsius on the hot plate that I have set up here, it is now beginning to form some bubbles and some water is starting to escape. And as soon as I put a watch glass on top of it, you can't see anymore because the bottom of the watch glass begins to fog up. If I speed this up a little bit, go at 30 times, I don't want to go too crazy here. So bump that up to increasing at a rate of 30 times for the reaction. You will see that it will continue to look wet as that moisture's leaving. I'm trying to break that up with a stirring rod, but after a while it starts to stick, sort of like concrete. And you have to go back and you have to break it up again. And now what you'll do at this point is start to use a glass stirring rod. I guess I should shave my knuckles when I'm going to do these kinds of videos so you don't see the hairs on my knuckles. But anyway, so I'm breaking it up. I'm trying to use a stirring rod initially here in terms of that setup, but I want to try to avoid at a point where it gets to the stage that it's pretty hard. If I use a stirring rod, I might break it. So I'm actually using a spatula, and I'm trying to break away the grip that has formed between the glass and the solid as the moisture is starting to drive out. So you scratch it, you break it up a little bit, you put it in, you twist it. You're trying to break that interaction between the magnesium sulfate and the silicon dioxide of the glass. So as you break this apart, and it's taking a little bit of effort to do this, what will happen is that it will eventually continue to dry out. You'll lose that last bit of moisture that's trapped inside there. And then when you're all finished, it should be a fine powder where it has lost the moisture that's there and it's not going to be attracted to the sides anymore. So as I get towards the end of this, and look at the results here, it's now more powdery. I can break it apart. This is where I am almost at a point of it being dehydrated. So I'll have to remass that once it's not sticking to the bottoms. Let it cool down first so that you don't have any convection currents above the beaker that's going to interfere with the reaction. And then after this, we will be able to heat it up a second time and remass it and see if it has lost any more mass. And you keep doing that until you get relatively a constant mass value. So let's stop at this point. I'm going to pause for a minute so I can take a look at what has happened to my manganese dioxide, and then we'll go from there. Now we end up with a solution of the manganese chloride. There still may be a little bit of vapors that are there from the hydrochloric acid, but most of it should be gone at this stage. We do have a watch glass on top of it, and what that's doing is it's recondensing some of the liquid. It's dropping back down into the beaker. So we get to a stage where we start to see some solid bubbles begin to form. So the gas is beginning to be released from underneath, a little bit of liquid that's left over. It starts puffing up a little bit. Here's where you want to be careful if you're using a Bunsen burner that you're not overheating, because then it would start acting like popcorn and it will begin shooting solid all over the place. Here, using a hot plate, I have the temperature here at about 150 degrees, so it's above the boiling point. Now it's a solution that has some ions in there, which elevates the boiling point beyond 100. So I can tweak it a little bit using the hot plate and adjust it to make it go a little faster, a little slower. At a stage where it keeps getting to a point where it drips from the top, what I'm going to do is come in and remove that watch glass. And I'm going to do that by just taking a pair of beaker tongs, come up from the bottom of the beaker along the sides, and then lift it off and set it over on a paper towel. Here we want to do the final heating, making sure that it's not popping and losing any solid. You don't want it shooting out of the tube. You'll notice that it has a pink color to this manganese chloride compound that we created. And it's the same thing like we did with the Epsom salt, where we had to heat it up to complete dryness. We have to do the exact same thing for the manganese chloride. So we have to heat it up until there's no more bubbling, obviously, but then we have to start breaking up the solid until we get to a point where there's nothing but powdered manganese chloride left. So let me pause for a moment my recording. I'm going to speed up the video to get a little further ahead. So I took off my watch glass. We are now proceeding in terms of looking at the pink solid that is there. Now I can wait a little bit longer, or if I'm impatient, I can try to start stirring it up, but I'm eventually going to have to get all that moisture out of there. So right now it's a little bit too gunky. So by putting my stirring rod down there and trying to mix it up, you can see what happens. It's all caking on the sides of that stirring rod. So I'm going to have to let it sit for a little bit. Then I'm going to heat it up some more, sit for a little bit. Towards the end, you have to bring in your metal spatula just like we did before and try to make sure we don't lose any of this pink solid that we have. And I'm going to speed up my video and then take a look at the results when we come to the final end. So I'm a little bit more impatient, so you'll notice that we're going at a little bit faster pace here. I'm heating it up, I'm stirring it, I'm grabbing it again, I'm moving it around. I try to scrape some on the top of the beaker. So patience, patience, my child. But you'll get to a point that it will be totally dry. It's going to be a very light pink versus having a darker pink color. Sort of when you're doing the titration with phenolphthalein, you don't want a deep magenta, you just want a wisp of the pink color. And here I brought in my metal spatula and scraped off the little bit of excess that was on my stirring rod. So I'm taking that into account. I'm losing a little bit of product. Now, the other thing that you might notice is that it's pretty clumpy at this stage. What I want to try to do is to break up those clumps. So I'm using my spatula, pushing down against the side of the beaker and trying to crush and break up any of the solid particles that I have, letting any moisture escaping and trying to break that up completely. If you really wanted to go crazy, you could take a mortar and pestle and actually grind that up, but we don't have to go that far. So now it's a matter of just massing the final product, taking a look at the results of what the initial mass was of the beaker, what was the mass of the manganese when you put it inside there based on adding it to the beaker, and now what's the manganese chloride, using that data to calculate the empirical formula. So as the normal experimentation, show all your calculations, give me a data table that shows your work, make sure they're clearly labeled, and then we'll see how well you do in terms of matching up what the expected empirical formulas are. We don't normally want to do confirmational labs and say, did I get the right answer? But in this case, there is a more acceptable correct answer, and we'll see how you do. So have a great day, and we'll see you next time.